Hi everybody, welcome to our July lecture series. So this lecture is part of our quarterly Head Start lectures. And if you haven't been to a previous Head Start lecture before, so what we're going to be doing for the next around 2 hours is that I'm going to go through as much of the term 4 stuff as I can possibly get through. So hopefully what happens is by the time you get back to school, you'll have a good understanding about these topics. And when you get back, hopefully you're able to apply the knowledge a lot better, and you just have an overall better understanding of these topics. Um, if you are watching this live, I suggest that if you have any questions, please put them in the chat below. Because I can guarantee that if you have a question, there's going to be at least one or two people with that same question. So if you have any questions, have the courage, put it down there, and I can answer them as soon as I can. If you're not watching this live, however, uh, you should also have access to the chat. So if you have any questions, just scroll down to the chat, and hopefully that question has been answered before. So yeah, hopefully that solves any confusions along the way. So first of all, a quick welcome from ATAR Notes, and thank you for joining in. Considering that this would be your last real school holidays, because your next school holidays, I can guarantee there are not going to be. It's not going to be any sort of holiday. It's going to be all exam revision and whatnot. So this is your real final school holidays. So yeah, thanks for joining in. And just a quick overview about what ATAR Notes provides. So we have a bunch of study notes, lectures, such as these ones. We also have a bunch of newsletters and articles and discussions. So if you have any questions, uh, yeah, discussion is a pretty good place to go to. And of course, everyone's favorite resource, the ATAR calculator. I know I use the ATAR calculator quite a lot in my year 12. Yeah, on top of that, ATAR Notes also provides a bunch of paid resources such as study guides, revision guides. We also have a bunch of practice exams, and I know that's going to be very important in the coming few weeks, coming few months. Yeah, so if you're interested in one of those, check the ATAR Notes website. Additionally, we also offer a tutoring service from TutorSmart, which is where I've been working for the past year or so. We provide uh, one-on-one tutoring, and we also provide group tutoring. So if you are interested in that, head over to the TutorSmart website or the ATAR Notes website. It should be there somewhere. Cool. So before we get started, I'll give you a quick overview about myself. My name is Ishan, and I graduated last year with a 98. With physics being one of my top subjects, I actually scored a 47 or 48 in it. And yeah, so since then, for about the past year or so, I've been tutoring with TwoSmart and AirTime Notes. And I've been doing a lot of these lectures and a lot of these revision lectures. On top of that, I've been tutoring physics, methods, and chem. So what we're going to be doing for the next 2 hours. Yeah, so these are the main around six topics for Unit 4. Yeah, so the thing about Unit 4, I'll admit, it's that it's very theory based. There's not much calculation. So if you've forgotten your calculator, you know what? That's perfectly fine. We're not going to be needing it. We're not going to be needing it. Uh, yeah. So the main question that we're answering in Unit 4 is what is light? We want to know, is light a wave or is light a particle? I'll give you a quick spoiler alert. Um, it's neither. It's both. Light is both a wave and a particle, and you'll see why that makes sense and why that kind of doesn't make sense. Yeah, we're gonna go through special relativity, uh, wave light duality, photoelectric effect, and Young's double slit experiment. All of these topics are new, and not only is it new, um, I'll I'll admit that these topics are definitely very heavy. Yeah, so in these 2 hours, if you're completely lost, if you have no idea what's going on, that's perfectly fine. Because yeah, these topics are very heavy, and there's no way that I can fully explain any of these in 2 hours. So yeah, so the point of this lecture is just to give you an overview about what to expect. If you don't understand these topics fully, that's perfectly fine. So when you get back to school, hopefully you'll have a better understanding. Yeah, cool. So we're gonna start off with waves. And so the question is, what is wave? What is a wave? And a wave is just basically a transfer of energy. I'll just highlight this. Transfer of energy without the transfer of matter. And when we're talking about waves, there are two types of waves that we care about. One is called a mechanical wave, and the second type of wave is the electromagnetic wave. And the key difference between an electromagnetic wave and a mechanical wave is that a mechanical wave requires a medium to travel through. So some examples of mechanical waves are sound, water, and slinkies. So for all these waves, you need some sort of medium for the energy to travel through. So for our sound waves, we need air. For water waves, you need water, and for slinky, well, you need a slinky. Electromagnetic waves, on the other hand, are special because they don't need they don't need a medium. So electromagnetic waves are basically all of our light waves. And if you remember if you've done it before in not unit 1, in year 11, where we talked about the electromagnetic spectrum, and that's that's basically all of our light waves, going from radio waves all the way to gamma rays, and that comes back in this lecture and comes back in unit 4. Cool. So when we're talking about waves, there are two things that we care about. One is called a wave pulse. And wave pulse is just a singular wave. So if you imagine this to be some water, wave pulse would just be a singular wave that travels through the water. When you combine multiple wave pulses and you create a continuous spectrum of wave pulses, you create something called a periodic wave. And this is probably what you've seen before. So you just have a bunch of waves, bunch of wave pulses coming together, and that's just creating one continuous wave. Cool. There's one thing I want to make clear. So let's imagine that this is a water wave. So this is, I'll do it in blue. Let's imagine that this is a water wave. The question is the water moving? I know it might seem like the water is moving, but what's actually happening is the water is not moving. Even though the wave is traveling in this direction, traveling to the right, the water is not moving. What's moving is the energy. The water is just traveling up and down. So if we have some water here and the wave comes, what's going to happen is that the water at this section is going to be lifted up and it's going to drop back down after the wave passes. The water is not moving from left to right. It's the energy that's moving left to right. Why? Because a wave is a transfer of energy and not a transfer of matter. So the wave is traveling this way, traveling to the right, and the water molecules are traveling up and down. And when we see something like this is what we call a transverse wave. Transverse, spelled that wrong. Yeah, I don't think I spelled that correctly, but it's a transverse wave. A reason why we call it a transverse wave is because the wave is traveling to the right, and the water molecules are going up and down. So the wave is traveling to the right, and the water molecules are going like this, going up, down, up, down, up, down. And because the direction of the wave, which is going to the right, and the direction of the particles, which are going up and down, because they're at right angles to one another, we call this a transverse wave. So a transverse wave is basically when the wave and the particles are moving at right angles to one another. The second type of wave we have is something called a longitudinal wave. So a longitudinal wave is when you have a wave and the particles and the wave is traveling in the same direction. And the most common example of this is sound waves. So this is what a sound wave looks like. So you have these sort of dots bunched up close together, and these dots are like air particles. And so you have these areas of compression, so when the dots are really close together, and you have places of rarefaction where the molecules are spaced out. And the reason why we call this a longitudinal wave is, let's assume that this is a sound wave and it's traveling to the right. What happens in a sound wave is that the molecules of, like the air molecules, they are oscillating left and right. They're going like this. And because the water, not the water, the air particles, they're oscillating in the same direction as the wave is traveling, uh, these two directions are parallel. So you have this direction, which is left, right, and you have this direction of the wave, which is going to the right. And because they're parallel, we consider this to be a longitudinal wave. Cool. And what you can do with waves is you can calculate the period of a wave and the frequency of a wave. So if you remember in your your term 2 stuff, where you did EMF graphs, it's kind of the same thing. So if you remember this, you had some sort of like sine wave. You had voltage in the x-axis, you had time in the y-axis. You had voltage in the y-axis, time in the x-axis, and you had some sort of voltage, like 5 volts up here, and then -5. And what you did from this is you could calculate the period and the frequency. So the period of a wave is basically how long does it take for the wave to complete one cycle. And in this case, since this is one complete cycle and it takes 0.5 seconds, the period of this wave is 0.5 seconds. Sorry, 0.5 seconds. The frequency is basically a measure of how many cycles can we complete in 1 second. So the frequency of this wave is going to be 1 divided by the period, which is 1 divided by 0.5, which gives us 2. And the units for frequency is given as hertz. Cool. Yeah, this is pretty much what you've done in your EMF graphs. Essentially, the exact same thing. Cool. There's a few terminology that you have to be aware of when it comes to waves. I'll go through the easiest ones first. So amplitude. Amplitude is basically how big the wave is. The more specific definition is the maximum displacement of the particle from its mean position. And mean position is basically when y is equal to 0. So if I draw a quick wave, the mean position is this sort of x-axis. That's the mean position. The amplitude then would be the maximum displacement from this x-axis to the top. So the amplitude is this. So if you remember back to EMF stuff, that's basically like your peak voltage. Wavelength is how far the wave travels in one period. So if this wave was, let's say, 2 meters long, the wavelength of this wave would just be 2 meters. Velocity is just basically how fast does the wave move. How fast does the wave move? And it's given in meters per second. And the thing about velocity is usually constant. So the velocity of sound waves is about 340 meters per second. You don't need to know that, but it's usually around that. And the thing is with the velocity, with the speed of waves, you can't really change that as much. And you end up with getting this formula. Velocity is equal to frequency times wavelength, which shows you the relationship between velocity, frequency, and wavelength. This second formula over here, so velocity is equal to wavelength divided by time, that comes from the formula that frequency is equal to 1 divided by time. So if you combine these two equations, frequency is equal to 1 divided by time, and you combine this equation with velocity is equal to frequency times wavelength, you combine the two, and then you get this. And to be honest, this is probably the only calculations that you're going to end up doing in Unit 4, especially when it comes to waves. There's this, and there's about 2 other formulas that you need to know. Yeah, so as I said, not many calculations for this subject, for this topic. Cool. Now that we know that, what we want to know is what happens when we have 2 waves interacting with one another. And when this happens, we call this a superposition. So in this case, we have 2 waves. We have this red wave and we have this blue wave. Yeah, they're traveling together. They're traveling towards each other. And the question we want to ask is, what is going to happen when these 2 waves collide with one another? And what happens is these 2 waves are going to combine and their amplitudes are going to add. So let's just say that this red wave has an amplitude of 5 and this blue wave has an amplitude of 3. So what's going to happen when these 2 waves come together and they meet in the middle? It's going to result in a much bigger wave that has an amplitude of 8. Yeah, so essentially these 2 amplitudes just get added to one another. So if instead, I'll rub that out. So if instead this wave, this blue wave, was underneath, so if our scenario looked something like this, let's forget about the top part for a second. If the blue wave was under the x-axis, then what happens? So when they combine in the middle, what we're going to see is these 2 waves are going to add, and it's going to result in a smaller wave. And the resultant wave, when these 2 waves combine, you're going to get something that looks like this. So essentially what's happened is we have an amplitude of 5 over here, we have an amplitude of 3 over here. So you can sort of think of this 3 as -3. And when you add 5 and -3, you're going to get a final amplitude of 2. And yeah, so that's basically what happens when you have 2 waves interacting with each other. So what happens after? So we know that these 2 waves, they're going to come, they're going to meet in the middle, they're going to combine. Depending on if it's positive or negative, it will depend if the wave is getting bigger or the wave will get smaller. Next thing we want to ask, or next thing we want to know, is we know that these 2 waves combine, right? And then what happens afterwards? So does this red wave go back the other way, or does this red wave keep going, or do they just cancel out? So what happens is that the 2 waves, they sort of pass each other, and they just continue as they were. So if you remember that this red wave that was on the right hand side, and this blue wave that was on the left hand side, they keep traveling and then just pass each other like nothing ever happened. In a perfect scenario, the amplitudes of this should remain the same. So if this had an amplitude of 3, this had an amplitude. We know that the red one had an amplitude of 5, the blue one had an amplitude of 3. Once they pass each other, the amplitudes should still remain. So this should have an amplitude of 5, and this should have an amplitude of 3. So essentially, it's just the same wave that have passed one another. And putting it all together in an animation looks something like this. Yeah. So if this blue wave was instead going underneath, it was reflected in the x-axis. Oh, I can't see that. If this blue wave was going like this, it would be the same thing, but in the middle, the resultant wave is going to be smaller, and the wave will just continue as they were. So if the wave on the right hand side keeps going to the left, you'll end up with something that looks like that. So the red wave that was on top remains on top. The blue wave that was on the bottom remains at the bottom. And so this brings us to this next thing about constructive interference. And put simply, constructive interference is just when you have two waves, they combine with one another, and the resultant wave is a lot bigger. So you can see that we have this wave. We'll just call this wave 1, and we'll call this wave 2. Let's draw this out. Yeah, so we have wave 1 and we have wave 2, and you can sort of imagine that as these two waves traveling on the same sort of string, or like the same, or maybe the same water or the same slinky. And what happens is, because of the way the waves are, these two waves, you can see, it's like the exact same wave. And when they're traveling, the amplitude of these waves are, the amplitude of these waves are going to add, and you're going to end up with a wave that is about double the original size. And we call this constructive interference. The opposite of this is destructive interference. So what's happened in this scenario? We have, again, we have wave 1, we have wave 1, we have wave 2, and when you add these two waves together, so if they're traveling together or if they're traveling towards each other, they're going to cancel out. And the reason they cancel out is, I'll just quickly show you. So if I just quickly sketch out the bottom graph and move this graph on top of the other wave. Yeah, it's not a pretty illustration, but this is what you get. So what's happened? We just got this graph, this wave, and we moved it up. And now what this results in is a flat line. And the reason we get a flat line is because if you add the amplitudes of every single position, you're going to get 0. Right. So if you look at this point over here, so if we have this negative, we have this positive, they add up, and we have 0. So essentially, we have like +3 here, and we have -3 here. They add up to 0. The same thing for this position. It's not, again, I'm not an artist, but it's essentially the same thing. We have a negative number, we have a positive number, we add them two together, and we just get 0. And yeah, so this pattern will occur at every single point of the wave. And when you have something like this, where the two waves perfectly cancel out, we call this perfectly destructive. Oh yeah, and we call this destructive interference. So to make sure that you don't get confused between constructive interference and deconstructive interference, is that you can think of constructive interference. You think of constructive. Constructive means you're building something, you're making something bigger. So, so constructive, you're making something bigger. So therefore, constructive interference is when two waves combine to create a bigger wave. And if that's the case, deconstructive interference would be the opposite. So deconstructive meaning you're destroying something, and so in that case, you're destroying the wave, you're making it smaller. And yeah, so hopefully with that, you won't get confused between the two. Cool. So I want you to look at this image. So what's happening here? I'll just quickly describe what's happening. We have some waves. These are some water waves traveling through the water. And over here, we have some barrier. And what's happened is that the waves are going in this direction. The waves are going in this direction, and what happens is when it hits the barrier, these waves are spreading out. So you can see that this is the first wave, the second wave, and the third wave. They are spreading out in this sort of shape. And this sort of spreading out effect is what we call diffraction. Yeah, so this wave is being diffracted and it's spreading out after it passes this gap. So this gap is also called an aperture. If anyone's interested in photography, It's kind of the same idea. So the gap is basically how far apart is this, this barrier. And depending on that and depending on the waves, that is going to impact diffraction. And diffraction, again, is just basically how much spreading do we have. Do we have? And it's the same sort of scenario here. So we have these waves. They've hit a barrier, and what's happened is that they've spread out, and it creates this sort of circular pattern. And yeah, you can see the same thing here. It's creating this sort of semicircle type of pattern. Yeah, one thing to keep in mind is this wave. So I can draw out this wave like this. So if that's a water wave, these sort of like white parts, that is essentially our crest. Yeah, so crest being this part, so that's our crest, and this is our trough. So these parts where we have this sort of white parts, that is our crest. So that's our maximum amplitude. Our trough is our like these dark parts where the waves are like going down. And the same thing that's happening here. So these white parts, these are our crests. So these bright spots, maximum amplitude, that's our crests. These dark parts, that's our troughs because that's like the darkest part of like the lowest energy of the wave. And what you can see is that the wavelength, so we have this wavelength here. The wavelength is the same even after being diffracted. And the same thing here. So the wavelength, well, whatever this wavelength is, that wavelength gets continued after it's been diffracted. And so what we can do, we can combine all this information, and we get this sort of formula. Extent is this divided by, extent is this, wavelength divided by the width. The thing is, this is not really a formula. The thing is, because diffraction is not something you can measure. Like you can't say, oh, this is diffracting by 200 or this is diffracting by half. Diffraction is sort of like a qualitative thing. You can't really measure it. And that's why we have this sign, which is the proportional sign. So what this is saying that the extent of diffraction is proportional to the wavelength divided by the width. Wavelength is just the wavelength of the wave, and the width is the distance between the gaps. So if this is our setup, the width would be this distance, the distance between the two gaps. Cool. The next thing you have to keep in mind is this is a ratio. So the extent of diffraction is like proportional, or it's like the ratio of a wavelength divided by the width. So if you want to maximize diffraction, you want this value, or the extent of diffraction, to be close to 1. You want that to equal approximately 1. So when that happens, you get this. And when the wavelength and the width are of equal value, the ratio is going to equal 1. It's going to be close to 1. And when that happens, you're going to get maximum diffraction. Again, diffraction being how much does the wave spread out. And so when the ratio is near 1, the spreading outness of the wave is going to be maximum. If, however, the width is bigger than the wavelength, because the ratio is out of whack, it's not close to 1, the amount of diffraction you're going to get is going to be a lot lower. And the same thing will occur if the wavelength is much bigger than the width. Because the ratio is not close to 1, you're going to get less diffraction. So for example, let's just assume that the width is 1. Let's assume that the wavelength is 1.1. 1.1 divided by 1 will give us a value will give us a value that's close to 1. And because it will give us a value close to 1, we're gonna see a lot of diffraction. But if the wavelength was really big, so let's say the wave was 200, this number is much bigger than 1. And because it's bigger than 1, we're not going to see much diffraction. Same thing will occur if we increase the size of the width. So if we make the width really big, let's say we make the width 1,000, we're not going to see much diffraction. And there's one thing I want you to keep in mind is diffraction can only occur on waves. So in other words, all waves can be diffracted. All waves can be diffracted, right? I want you to keep that in the back of your mind. So if you're making notes, yeah, just keep this in the back of your mind for a second, because it's going to be very important for the next topic, which is light as a wave. So just a quick history lesson is that in the 1800s and the 1900s, we didn't know much about light, and back in the day, it was assumed that light is a particle. But there was also a bit of evidence for light being a wave. And so there was lots of debates in the science community to figure out, is light really a wave or is light a particle? And so some smart guy, Maxwell, he decided that light is actually a wave. And he called it the electromagnetic wave. And you'll see where that name comes from. And so what he proposed was that light is actually light is actually the acceleration of an electric charge. So this is what he proposed a light wave to look like. So we have some electric charge, we've accelerated it, and what happens when we accelerate an electric charge, it's going to create an electric field, right? And going back to our term 2 stuff, right? So if we have, let's say we have a wire, we have current going that way, so that's our electric charge is traveling upwards, right? And if electric charge is going upwards, what we can do is we can use our right-hand thumb rule and we can calculate the magnetic field that's being created. So applying that same logic, right? So if accelerating an electron, accelerating a charge creates an electric field, that electric field is also going to create a magnetic field, right? So yeah, we have an electric field, and that electric field is going to create a magnetic field. Cool. But when you have a magnetic field, right, going back to, again, unit 2 stuff, when we had the motor, not the motor, we had the electrical generator. So we had a coil spinning around a magnetic field. And what that did, that created an electric field, or that created a current or an electric field. And what we said before was that electric field is creating a magnetic field, and this magnetic field is creating an electric field. And this cycle just keeps going and keeps going and keeps going. And because of this, we call light, Maxwell called light a self-propagating or self-sustaining wave. So essentially, this wave a light wave can travel forever. Because it doesn't really need its source of energy. You can't say the same about a water wave, right? So if you have a water wave, the wave is going to die out after a while. Why? Because the energy is going to get wasted in the form of sound and heat and whatnot. But because light sort of creates its own propulsion, light can go on forever. And we can know this because light has been traveling for what, 14 billion years from like galaxies really far away. And yeah, so light is self-propagating, meaning it can go on forever. The reason why mechanical waves are not self-propagating is because, one, you need some sort of energy to for the wave to travel across the medium, right? So if you have water or a slinky, right, you need energy to push the energy through some sort of medium. And eventually, the energy is going to die out. Like a wave, it's not going to go on forever. Eventually, it's going to die out. But unlike electromagnetic waves, which don't need a medium, they can just go on forever. Yeah, so he proposed that the electric field and the magnetic field, because they're orthogonal, orthog, orthogonal. I have no idea if that's how you say it, but essentially that's just a fancy word to say perpendicular. Yeah, so because the magnetic field and the electric field is perpendicular, um, they can sort of induce one another. So we have the electric field creating magnetic field creating electric field, and so on and so forth forever. Um, cool. So this diagram is actually quite important, and this is something that should go on your cheat sheet. Yeah, just a second thing to keep in mind about light waves or electromagnetic waves is that these are transverse waves. Let's not use the word transverse. These are transverse wave. The reason we call it transverse is because the light is traveling in this direction, and the particles, well, it's not really particles, but the energy, the energy is sort of propagating perpendicularly to the direction of travel. So the light is traveling in this direction, and the energy is going perpendicularly to the direction of travel. And because it's perpendicular, we call this a transverse wave. Cool. So if light is a wave, right, and going back to this equation before, like velocity is equal to frequency times wavelength, right? So if light is a wave, then surely we can apply this same formula to light. And that's the thing, we can do it. And we get this formula, which is c is equal to frequency times wavelength, which is the exact same formula. It's just that velocity has been swapped out for the speed of light. So if you ever see c, that's basically the speed of light, um, speed of light, which is 3.0 times 10 to the 8 meters per second. So essentially this formula is saying 3 times 10 to the 8 is equal to frequency times wavelength. Again, same formula, it's just the velocity has been swapped out for the speed of light. Yeah, so next thing we have to keep in mind is that the speed of light is always constant. Speed of light is always constant. So velocity is equal to frequency, velocity is equal to frequency times wavelength. If velocity is constant, and let's say we were to increase frequency, if we were to increase the frequency, what is going to happen to the wavelength? Well, the wavelength is going to decrease. And vice versa, if we were to increase the wavelength, the frequency will decrease because frequency times wavelength has to be constant, and that constant is the speed of light. And so applying that same logic to this. So this is our electromagnetic spectrum. You don't have to memorize this by heart because, again, you have a cheat sheet. This is something that has to go on your cheat sheet. So you can apply the same sort of logic. So we know velocity is equal to frequency times wavelength, and we know velocity is constant. So for radio waves, so radio waves have the longest wavelength. So yeah, radio waves have the longest wavelength. So if radio waves have the longest wavelength, they're going to have the shortest frequency. So longest wavelength, shortest frequency. Why? Because these two, the frequency and wavelength, is inversely proportional. If you increase one, the other one has to decrease. So similarly, if you go to the other side, if you go to the gamma rays have one of the shortest wavelengths. And because the wavelength of a gamma ray is very, very small, the frequency of the gamma ray is very, very high. And this is why like this stuff, like the gamma rays and the X-rays and the ultraviolet rays, these are very dangerous because they have a shorter wavelength. And a shorter wavelength means that the frequency is going to be much, much higher. On the other hand, all these radio waves, microwaves, and whatnot, because they have such a long frequency, yeah, some of these radio waves can have like 100, 200 meters of wavelength, and because it's so big, the frequency is a lot lower. And because the frequency is a lot lower, the energy of the light, so the light energy is, so the energy is a lot lower. And that's why that's why you don't get harmed by radio waves. But if you were exposed to gamma rays, you're not going to live for very long. And so just a quick question to consolidate this idea. What is the frequency of visible light which has a wavelength of 650 nanometers? And when it comes to this sort of questions with frequencies, wavelength, the most common unit that's given to us is nanometers. Nanometers is 10 to the negative 9. And if you don't know what, if you often get confused between what each sort of unit is, on the bottom of your cheat sheet, there is this section of metric multipliers. And then what it tells us like what pico is 10 to the 12, nano is 10 to the 9, mega is 10 to the 6. So if, let's say you've completely forgotten what a nanometer is, you can go to this page, the last page of your formula sheet. You can go to nanometers and say, nanometer is 10 to the 9, or 10 to the negative 9. And so obviously you want to convert all your units into SI. So the frequency, which has a wavelength of 650 nanometers, that is basically 650 times 10 to the negative 9. We also know that velocity is equal to frequency times wavelength. The velocity of light is always constant, which is 3 times 10 to the 8. The frequency is, the wavelength is 650 times 10 to the 650 10 to the negative 9 times the frequency, and that gives you a final answer of frequency is equal to 462 times 10 to the 14 hertz. And if you really want to be fancy, that is equivalent to 462 terahertz, which is THz. Don't need to know this. It's like a little fancy FYI. Yeah, this more than enough. Yeah, hopefully I've done the calculation correctly. So if anyone wants to double check that, yeah, feel free. Cool. So here's the thing, right? So Maxwell, he proposed this idea that light is actually a wave. And then what he did, assuming that light is a wave, we can apply these waves. But the thing is, there wasn't any conclusive evidence that light is a wave. It was mainly just theory at this point. And so what the physicists wanted to do is they wanted to actually verify, is light a wave, or is this just a random theory? And so this brings us to one of the most famous experiments of like physics. Cool. So if you remember back just a few slides ago, I told you that all waves can be diffracted. Right. I just want you to keep that in the back of your mind, just for the next few minutes. So going back to the original thing of diffraction of waves, right? So this is what a diffraction of wave looks like. So we have some setup that looks like this. We have water wave, any wave going like this. When it hits the barrier, it sort of spreads out in this sort of like Wi-Fi shape, right? So that's what's happening. So applying that same logic to this sort of setup. So instead of one slit, what's happened is we've made two splits. So essentially, you can imagine this looking something like this, right? So this is what our new setup looks like. So imagine that we have water waves. With water waves that are coming like this. Water waves that are coming like this. And what's going to happen is when it hits the barriers, it's obviously going to diffract. Like we know that because these are water waves, and water, obviously, it's a wave. And what's going to happen is at this point, it's going to diffract. We know that because when a wave hits a gap, it's going to diffract, right? We know that. When it hits the second gap, the same thing is going to happen because it's a wave hitting a gap, and when that happens, it's going to diffract. And you sort of get these two Wi-Fi shapes. Cool. So what this guy, his name is Young, I think it's Thomas Young. He made this experiment. So what he thought, because this was during the time where it was thought that light is a particle. Light is a particle. That's what a lot of people believed. And Thomas Young also believed that. So what he wanted to do, he wanted to make this experiment to disprove that light is a wave. And essentially, he made two slits, really, really small slits, and he shot a light through it. And the theory was that if light is a particle, this is what you're going to see, right? So you can, instead of a particle, you can imagine light to be I don't know, some tennis ball, right? And these slits to be a door. If you throw a tennis ball through a door, obviously it's not going to diffract, right? It's going to go straight through the door. It's going to go. Oh yeah, you have some door. You throw the tennis ball. It's going to go straight through. That seems like common sense. And then that's what people thought. They thought that since light is a wave, when the light passes through the slit, it's just going to go straight through. And what you're going to see on the edge, or on the wall, is this, right? So you can imagine, like, we have these tennis balls going through this one window, and we have tennis balls going through this other window, and these tennis balls keep going, and they hit here, and the tennis balls from here, they go there, right? That seems like it makes sense, right? But the problem was that's not what happened. So this is what was expected, right? If light was a particle, it's not a particle. Light was a particle. This is what you would see, right? And again, it makes sense. Like, you're throwing a tennis ball through a door, and that's what you're going to see. But that's not what happened. What Thomas Young saw, this is what he saw. So again, this is what we expected, but this is what he saw. So essentially, there's a bunch of like spaghetti sticks of black and white. So if you assume that, let's just assume that this is white light. The white light hits the barrier, and what's going to happen is there's going to be like sort of sections of white light, and there's going to be sections of darkness, and there's going to be sections of white and darkness. And the question is, like, why does this happen? Like, how did this happen? Because this is what was expected, and then why does this happen? So yeah, so this sort of phenomena was described, was explained by light being a wave. So essentially, what happened was, you have light that's traveling through the waves, traveling through the gap, and this light is diffracting. This light is diffracting. So you imagine that this is all the light waves, and light waves sort of diffract. And what happens is, if you combine the two, so like this is what we see with a single split. If you were to do a double split, right, you can sort of imagine this duplicated down here. So if this is the same wave, you're going to get something. You're going to get this, because again, it's a double split experiment. There's 2 points of diffraction, and what happens is, these two waves, they are going to form constructive and deconstructive interference when they reach the wall. So imagine if this is our wall. Yeah, on the wall, they're going to form constructive and deconstructive interference. And so what you end up getting is something that looks like this. So imagine that, like, you can imagine that, let's imagine that this is our wall. And let's say this is the center of the wall. let's do it again. So imagine this is our wall. This is the center of a wall, and so this is what Thomas Young saw. So in the middle, you would see a bright light, and next to it, you would see like a dark band. You imagine that's filled out. I just can't be bothered doing it now. And then after that, what you would see, he would see another bright band, and then next to that, he would see a dark band, and then again, he would see another. You'll see a white band. You see a white band, and then the same thing on the left-hand side. You'll see a white band and a dark band. And then this is what he saw. He saw this sort of there's this sort of zebra pattern, and this zebra pattern is what we call an interference pattern. And so what happened? So what happened was, so these are two splits, right? The waves, the light waves, have diffracted, and they've sort of spread out, and they spread out at this position and spread out at this slit. And what happens is when they reach the wall. So I'm just going to, just for reference, I'm going to say this is the center. This is D1, so dark 1, dark 2. This is our dark 2, sorry, dark 1, dark 2, dark 1, dark 1. This is our dark 2, and this is our dark 3. And the middle, we have light 1, light 2, light 2, light 2. So this is our center. So next to the center, we have two dark patches, and then next to that, we have two light patches, and then two dark patches, and then light patches. So what's happened is that in the center, we have something called antinodal lines. Antinodes basically is just a fancy word to say constructive. Yeah, antinodal lines, constructive lines. But in this scenario, we like to use the words of antinode and nodes. Yeah, so in the middle, we have constructive interference, or antinodes. Next to that, so this is our center, right? And next to that, we have two dark patches. So we have dark 1 and dark 2. And this is our dark 1. Sorry. This is a dark 1, and we have like another dark 1 next to it. After that, so this is a dark 1, this is a dark 1, and next to that, we have another patch of bright light. And this bright light, we can call this as L1, L1. And then that pattern just goes on so on and so forth. So after this light patch, we have another dark patch. And this sort of pattern just keeps going across. Yeah, so antinode is constructive interference, and nodal lines is what happens when we have deconstructive interference. It's a bit confusing to remember the two, but the one way I used to think about it is nodal lines. So nodal lines, no, we have nodal lines, and you have no at the front, no meaning no, and so nodal lines means no light, and an antinode would just be the opposite, so light. You're actually having light, not darkness. And yeah, so this is essentially what happened. And so what that proves definitely that light is a wave. And because remember what I told you before, that all waves can diffract. So all waves can diffract, right? So if what Thomas Young showed, or what he proved, was that light is in fact diffracting. It's showing a diffraction pattern. And since only waves can diffract, light therefore must be a wave. And so yeah, he essentially proved that light is a wave. Why? Because light diffracts, and diffraction is a wave-like property. this. So essentially, light's diffracting, and only thing that can diffract are waves. Therefore, light is waves. And that's pretty much what he proved. If you're answering a question, the most common question with this is something along the lines of what does Thomas Young's experiment show about the wave-like nature of light? And then you would say something along the lines of Thomas Young's experiment shows that light is diffracting, and diffraction is something that is a wave-like property. Yeah, and you would talk about his results in the experiment, showing that his experiment showed that light was diffracting, and it created an interference pattern with nodes and antinodes, which basically means that a light is diffracting and diffraction is wave-like property, so light is a wave. You would say something along those lines. If you want, you can actually write that down on your cheat sheet, something like that, but obviously a better version of that, and you'd probably just copy paste it. Hopefully that should be fine. Because again, those types of questions, when you start doing exam preparation, you'll realize that those type of questions are very, very common. Yeah, so what Thomas Young, the next thing he found was that the intensity of the light is greatest at the center. And it gets dimmer and dimmer as you move out. So going back to this diagram, so what he saw that the center of, so this is our center, so in between the two gaps, the center is always the brightest. And as you move out from the center, the brightness of the bright bands start to decrease. Yeah, that's one thing he found. The second thing he found was that the fringes, or the fringe is another word for bands. So this is one fringe, this is another fringe, this is another fringe. The fringes were equally spread out. And what he found, so what he found was that you can get this formula, where x is equal to wavelength times length divided by distance. So what this tells us is wavelength is the wavelength of light, distance is the gap between the two slits, and length is the distance from the apparatus to the wall. And all of this will give you a distance of x. And what x is basically distance between two light bands or two dark bands. All right, so going back to our diagram before, so again, so let's say this is our center. This is our dark band. Then we have a light band next to it, and then another dark band, and another dark band, or in other words, fringes. And so the distance between one bright band and another bright band, so this distance, is equal to x. And the distance from one dark band to another dark band is also x. And essentially, it's the same distance because the size of the fringes, I didn't draw them properly, but in actuality, the size of the fringes are the exact same. So the distance between here and here, and the distance between here and here, is the exact same. And that distance is given by x. Yeah, so again, if I drew them properly, the spaces between dark and light should be even. And this formula, again, is on your formula sheet, and this is how you would use it. Cool. So we know that there's bright bands and the dark bands, right? But why does that actually happen? Like, why are we getting bright bands in the middle? But why are we getting bright bands in the middle, but not dark bands? Like, why are we getting dark bands here, but not light? So the reason why is because of something called path difference. So going back to what we did like at the start of the lesson with superposition. So it's basically that. So if you imagine we have these two waves, right? And if these two waves are traveling together, we say that these two waves are in phase. The reason why they're in phase is because one, they have the same amplitude, they have the same wavelength, and it's sort of the same wave traveling together, right? So, yeah, so this wave and this wave are the same wave, they're just traveling together. And if these two waves meet, they're going to constructively interfere. And we know that because I'll just draw out this wave. If these two waves are traveling together, right, it will look something like this, right? And since these are two different waves, the amplitude is going to add up, and you're going to end up with a wave that's about double the size. Cool. Yeah, hopefully that's pretty straightforward. But here's the thing. So if I take this green wave and I move it to the right by one wavelength, and so one wavelength is the distance from here to here. So that's one wavelength. If I move this green wave to the right by one wavelength, what do you think is going to happen? So if I move this by one wavelength, and if it loads, yeah, cool. What you see, well, if I drew it properly, but what you see, it's the exact same wave, right? It's the same situation from back there. It just moved one wavelength across. And because it's moved one wavelength across, and it's the same wave, these two waves they're still going to constructively interfere. Why? Because again, it's the same wave. They're traveling in phase, they're traveling together. So these two waves, they're going to constructively interfere, and you're going to get a bigger wave. Cool. Now what happens is if we move the wave by another wavelength. So this is another wavelength, and let's move the green wave by another wavelength. So let's move it down here. Again, since it's the same wave, they're traveling together, they're going to constructively interfere, and they're still going to constructively interfere. And if you move it another wavelength, so if I draw out another wavelength, that's one wavelength. If I move the wave by another wavelength, it's still going to constructively interfere. Yeah, just a quick aside that this purple line, that purple line is going on forever. So you can just imagine that this line is going here, it's going here, it just keeps going. Same with the green wavelength. So that wavelength it keeps going on forever. But the thing is, it's still going to constructively interfere because it's the same wave. They're traveling together. And so what we say is that if you have two waves and they have been translated by n wavelengths, where n is a whole number, they are still going to constructively interfere. Because again, we showed this before. When we moved the wave by one wavelength, and when we moved it by another wavelength and another wavelength, it's still constructively interfering. Yeah, so if we move the wavelength by a whole wavelength, move the wave by a whole wavelength, it's still going to constructively interfere. Okay, now we're going to do something slightly different. So we have this wave. I'll draw it out properly this time. Cool. We have these two waves traveling together, and they're constructively interfering. Cool. Now let's move the wavelength by half a wavelength. So this is the distance of half a wavelength. And let's see what happens if we move the green wave by half a wavelength. You get this. And the thing is, if you add these two waves together, right, these two waves are deconstructively interfering. Because if you add the amplitudes is going to add up to 0. And what you're going to end up with, a flat line. And the same thing happens if I move the wavelength by another wavelength. So we moved it by half a wavelength. Now we're moving it a full wavelength. So this is half a wavelength. This is half a wavelength. This is then 3/3. Sorry, 3 on 2 wavelengths. So if I move the green wave by another whole wavelength to here. Again, it's the same thing. It's deconstructively interfering, and we're going to be left with a flat line. And again, the same thing happens with the constructive. If we keep moving it by a whole wavelength, we're going to end up with the same scenario of deconstructive interference. Yeah, so when this happens, we say that the waves are out of phase. You can sort of think of phase as like out of sync. So before, since the waves were going sort of in sync, it creates constructive interference. But since these two waves, they're out of sync by half a wavelength, it creates deconstructive interference. Yeah, and essentially every time we move a wavelength by n minus a half wavelength, it's creating deconstructive interference. So when we moved it by half a wavelength, that created deconstructive. When we moved it by 3 on 2 wavelength, again, that was deconstructive. If we were to continue the pattern, then 5 on 2 wavelengths is also deconstructive, and so on and so forth. And it's given by n minus a half. But the thing is, why am I going through all of this, right? It's because of this, something called path difference. And essentially, path difference is the distance from the wave or the wave source to some point. It's given by this formula. So S1 minus S2, where S1 and S2 is the distance the waves travel. So S1, the distance S1 travels, S2 is the distance S2 travels. And just looking at this graphically, S2 is obviously going to travel a longer distance than S1. And then the distance, the extra distance that S2 has to travel is given by this formula. So essentially, you're just subtracting distances. So let's say this travels 5 meters, this travels 7 meters. The path difference would then be, path difference is equal to 5 minus 7, which gives us -2. And because we're taking the modulus of it, it's just 2. And if anyone's not doing spec, modulus just means just take the value. So if it's a negative number, just take the number that's there. Yeah, so the path difference is 2. Essentially, what we're saying is the second wave has to travel an extra 2 meters than the first wave. That's all that we're saying. So here's the thing. In this scenario, if we were to calculate, let's say the wavelength of this wave is, let's say it's some water wave, and the wavelength is 2 meters. What is the path difference between these two waves to this position? The path difference here is actually 0, because this P is at the center of the two splits. So like P would be like it's in the middle of the two splits. Because it's in the middle, S1 and S2 are traveling the same distance. So if they're traveling the same distance, the path difference is 0. So let's just say S1 travels 10 meters, S2 travels 10 meters, 10 minus 10 is 0. The path difference is equal to 0. And because the path difference is 0, the waves are going to arrive in phase, and constructive interference will occur. But let's see what happens if we have some different scenario. Again, let's say the wavelength is 2 meters. Wavelength is equal to 2 meters. Let's say that S2 travels, so this is S2, so this is our S2 wave, this is our S1 wave. Let's say S2 travels 8 meters and S1 travels 4 meters. The path difference, so how much extra did the wave 2 have to travel? So the path difference is given by 8 minus 4, which is just 4 meters. So S2 had to travel an extra 4 meters. What does this mean? So you can sort of imagine this as like, so I'll do it in different colors. So let's say this is S1. Yeah, let's say this is S1, and we'll say this one is S2. So this is S1, um, S1, S2. So wave 1 and wave 2. What's happened is that wave 2 has had to travel an extra 4 meters. So since we said the wavelength is 4, if the wave has to travel an extra 4 meters, we are shifting the red wave to the right by 4 meters. Or essentially, we're shifting it to the right by 2 wavelengths. So this is 1 wavelength, and that's what happens when you shift the wave by 1 wavelength. And a second wavelength going to end up here. And you can see these 2 waves are going to constructively interfere. They're going to constructively interfere because even though the second wave is 4 meters short, or it has to travel 4 meters longer, the 2 waves are still in phase. They're still in sync. And because they're still in sync, they will still constructively interfere. And because they're constructively interfering, we're going to get a bright spot. Hopefully that makes sense. So again, since we said the wavelength is 2, from here to here, that's 2 meters. And from here to here, that's 2 meters. And since the secondary wave is travels 4 meters longer, the secondary wave has to be shifted by 4 meters. And when that happens, you get this, which is still constructively interfering. And essentially, you end up with this formula, which is path difference is equal to n times wavelength. So if the path difference is a whole number multiple of the wavelength, you're going to get constructive interference. Because in this case, we had a path difference of 4, or we had a wavelength of 2, which gives us an n value of n is equal to 2. And because n is a whole number, n is a whole number, we're going to get constructive interference. Cool. Yeah, hopefully that's making sense. If you have any questions so far, yeah, put them down. The second thing that can happen is if we have deconstructive interference. Cool. So again, let's say our wavelength is 2 meters. Our wavelength is equal to 2 meters. Let's say S1 has to travel 5 meters. And let's say our S2 has to travel 8 meters. Again, I think you can see where this is going. So the path difference is essentially this number minus this number. So our path difference is equal to 3. And so I'll just quickly draw out. So these are our 2 waves traveling. We have a path difference of 3. So the red wave, you know what, just for the sake of argument, I'll just say it's traveling, this is a distance of 6. Just to keep in sync with the slide, we'll say we have a path difference of 1, because 6 minus 5 is 1. And yeah, cool, everything else is still the same. Yeah, so this is our red wave, the secondary wave, and the blue wave underneath is our S1. And because we have a path difference of 1, and the wavelength of a singular wave is 2, the red wave gets shifted by half a wavelength. So our red wave ends up being like this. And again, because you have positive negatives, this thing is going to cancel out, and you're going to get 0, or you're going to get a deconstructive interference. And the formula for this one is path difference is equal to n minus a half. And again, that makes sense because we got a path difference of 1. We've got a path difference of 1, n minus half times the wavelength, which is 2. And then you get half is equal to n minus half, n is equal to 1. And for this to be true, n has to be a whole number integer. And since we show that n is equal to 1, and since this is half a wavelength out of phase, or half a wavelength out of sync. It's half a wavelength out of phase, or half a wavelength out of sync. It's going to deconstructively interfere. And the same thing is going to happen if we have 3-on-2 wavelength or 5-on-2 wavelength. It's the same thing. And yeah, so this basically sums up everything about path differences. So path difference, again, is the distance between S1 and S2, depending on how much longer one of the waves had to travel. Constructive interference will occur if the path difference is a whole number multiplied by a wavelength, well, by the wavelength of the light or the wave. And deconstructive interference is going to occur when the path difference is n minus a half times the wavelength. Yeah, so the thing is, here's two formulas about constructive and deconstructive interference. They work with all sorts of waves. It works with every wave. And the thing is, you can do the same sort of experiment, but instead of using light, you can use speakers. And so if you have two identical speakers set up, playing the same sound, you're going to see the same sort of effect. So you can imagine we have these two speakers, and in the middle, you're going to have some really bright, or you're going to have some really loud music. But if you move to the next sort of fringe, it's going to be very quiet. And then the next fringe after that is going to be loud. And that that sort of pattern is going to keep continuing. And again, like was said before, the intensity of the sound will decrease as you move further out from the center. Cool. And yeah, so just to quickly sum up, what Thomas Young showed is that light. He showed that light is diffracting, and light's diffracting, and when light diffracts, it's going to create positions of constructive and deconstructive interference, which again is a wave-like property. So this is a wave-like property. Cool. Yeah, so since he showed that light is able to diffract, that pretty much proves wholeheartedly that light is actually a wave. And with that, that was pretty much conclusive evidence that light is a wave. And yeah, just a quick note, when you're answering questions about Thomas Young, you want to be talking about interference patterns and constructive and deconstructive interference, because interference patterns and these constructive and deconstructive, they prove that light is actually diffracting. And if light is diffracting, then it has to be these things show that light is diffracting. And if light is diffracting, then it has to be a wave. And essentially, that's how you would answer these worded questions. Cool. So that's everything about waves. The next thing that happened was that some scientists were not very happy because, again, this was a time during when light was believed to be a particle. And so the next sort of advancement in physics was this thing called the photoelectric effect. And so if you remember from term 2, you did something called the photovoltaic cells, which essentially was a very fancy word for solar panels. And so what the photoelectric effect is basically it basically tells us how solar panels actually work, or how photovoltaic cells actually work. And essentially, this is what's happening. So we have some light, and over here there is some metal, and when this light hits the metal, so first of all, we have the circuit, and this circuit's been cut up in the middle, and in the middle we have some sort of vacuum. It's called a cathode ray cathode ray tube. So in the middle, we have this thing called, I'll just quickly write it down. A cathode ray tube, something like that, yeah. A cathode ray tube. And when the light hits the electrons, essentially the electrons get displaced, and the electrons are going to travel to the anode, and it's going to create a circuit. So electrons go here, come here, and we have the circuit being created. First of all, for anyone who's doing chem, anode and cathode over here is not the same as the chem anode and cathode. So please don't confuse the two. The anode and cathode in physics has no connection to the chemistry one. So please don't confuse the two. In this case, in photoelectric effect, the anode is positive. The reason the anode is positive is because the electrons have to go from here, and the electrons have to travel from this left side, and they have to go to the right-hand side, and that can only happen if the anode is positive and the cathode is negative. And again, in chem, it will be the other way around. So that's why you don't want to mix up chem and physics. Yeah, so cool. And just a bit more terminology for this stuff. Yeah, so we have a metal tube at the cathode, which is over here. We have some metal. We have a monochromatic light. So monochromatic meaning a singular wavelength. You can have multiple wavelengths. It's just that, just to keep things simple for VCE, we just assume that the light is going to be monochromatic, and it's shone onto the cathode. We have an ammeter to detect how much current is being created, because again, when the light shines on the metal, it's going to complete the circuit and it's going to create some sort of current. And then we have this thing called a variable voltage, and basically it's just this little thing over here. It's like a battery, and it's like a power source, and you can pretty much change the amount of voltage that this power source is producing. And yeah, it's a thing called forward potential and reverse potential. Forward potential is essentially when the current is working and the light is actually creating current. So the forward potential would work in this direction. So the electrons are going from cathode to anode, as they should be doing. The reverse potential is the opposite. So the reverse potential travels in this direction. And this is controlled by this variable voltage. And I'll show you why that's important. So the thing was, when the light was getting shone onto the electrons were getting ejected. So you can imagine we have electrons here, and all of these electrons, they're getting ejected. What the scientists wanted to calculate was how much energy do these electrons have. Yeah, these electrons called photoelectrons. Photoelectrons are basically a fancy word for saying fancy word. Why can't I write? Oh, yeah, fancy word for saying electrons ejected by light. And so these electrons, they are traveling from here to here, and because they're traveling, they obviously have a velocity and they have some sort of energy. What we wanted to calculate was how much energy does the electron have. But the thing is, it's a bit difficult to calculate how much energy an electron has. So what the scientists did is, all right, so you can imagine this. So let's say we have some force. Let's say we have a force in this direction of n newtons. We don't know how much force. We don't know how much force that is. But what you can do is you can apply a force in the opposite direction, and you can change the amount of force. So let's say you put 50 newtons of force. Say you put 50 newtons, and you put 100 newtons, and you put 200 newtons. What you want to find out is what amount of force is going to match this. It's going to match this amount, right? So what you would do, you would try out your push with different forces until the red and the green is going to cancel out. So let's say, for example, if this is 75, right, but you don't know it's 75, but let's say it is 75. So if you push with 75 newtons, these two things will cancel out. And then from that, you would know that the red line has exactly 75 newtons. And so that's basically what the scientists did. They used a reverse potential and they shot, so the current of the photoelectrons is going to the right. It's going this way. It's going clockwise. But what the scientists did with reverse potential, they induced a current going in the opposite direction. So this is what they did. Yeah, so they created current going anti-clockwise. And what they did is that they changed the voltage until there was no current. Right? So if there's no current, that means the voltage, that the reverse potential is the same as the forward potential. So there's no current being formed. Because again, the electrons are being balanced out by the opposite force of the voltage. And so this is called the stopping voltage. So essentially, how much voltage do we need? How much voltage do we need so that there is no current being formed? And so this is how we can calculate how much energy the electron has. So from unit 3, we know that voltage, that work is equal to Q times V, where Q is your charge and V is your voltage. In this case, since the reverse potential is creating current in the opposite direction, the charge is equal to the charge of an electron. So this E would be 1.6 times 10 to the negative 19. So now you get this formula where work is equal to charge of an electron times the stopping voltage. And all of this is equal to kinetic energy. And this is something you've done in term 2, right? So since the electrons are being ejected with some sort of velocity, they obviously have kinetic energy. And the kinetic energy of the electron is now equal to E times V, where E times V is basically the stopping voltage going in the opposite direction. Right? So we want to cancel out the two forces until we get 0. And that's basically where this formula is derived from. Oh, and yeah, this point, stopping voltage will stop even the fastest moving electrons. So you can imagine that these electrons, they're being shot to the other side. And the stopping voltage is exactly the amount that you need to stop every single electron. And so let's say the stopping voltage is 2 volts. Using exactly 2 volts, you can stop every single electron from going from here to there. And there's another unit to calculate energy, and it's a non-SI unit called the electron volt. And because you can see, if I go back, since we're multiplying everything by 1.6 times 10 to the negative 19 a lot, just to help out, we use a different unit called the electron volt. And the electron volt is how much electron volt is this. Okay, so electron volt is how much energy does an electron have if it's charged with 1 volt. So 1 coulomb of charge is accelerated through a potential difference once, it gains energy. When 1 electron is accelerated through potential difference of 1 volt, it gains 1 electron volt. So again, we have W is equal to QV. The charge of the electron is 1.6 times 10 to the negative 19. The voltage is 1, in this case of electron volts. And all of this is equal to 1 electron volt. Yeah. Sorry, Oh yeah, all this is equal to 1 electron volt. And if you want to convert between the two units, so let's say we have joules here, we have electron volts here. To go from joules to electron volts, you have to divide by, wait, yeah, divide by 1.6 times 10 to the negative 19. And to go the other way around, it would be 1.6 times 1.6 times 10, what times 1.6 times 10 to the negative 19. Yeah, hopefully that's right. So with this topic of photoelectric effect, your units can be given in either joules, or they can be given in electron volts. And your job is to convert between the two, depending on which is more feasible. Uh, cool. So when this person, what is his name? What is his name? Right. So whatever scientist this person was who created the photoelectric effect, they found a few few things. So what the guy did, right? So we have this light that's shining on the cathode. What he did, he swapped out the lights. He tried out different lights and saw what happened. What he thought was that every single light should be able to produce some current, right? So he thought that doesn't matter what light you use, it will create a current and it's going to displace the electrons. But that's not the case. That's not the case because of something called the threshold frequency. And threshold frequency is what I like to call like the get out of bed energy. Let's say that the threshold frequency is 100 joules. If your light has less than 100 joules, let's say if your light has 90 joules of energy, it doesn't matter how much light of 90 joules you put. The threshold frequency, since it's lower than the threshold frequency, there's going to be no electrons being emitted. So, yeah, because it's less than a threshold, it's not going to create any current. So, if you want to create current, you have to shine a light that has a greater frequency than the threshold frequency. So, you need light that has 120 joules of energy. The second thing he found out that increasing the intensity of the light increases the number of photons, which, as you'll see later on, will increase the current. And he saw that the photoelectrons were released immediately. And the reason this is shocking is because at the time, these were the predictions. So at the time, it was thought that every single frequency, according to their knowledge of light, it was assumed that every single frequency of light should be able to emit photoelectrons. So it doesn't matter what, the frequency is essentially the color of light. So they thought every single color of light should be able to produce photoelectrons. But that's not the case because according to the experiments, there was something called the threshold frequency. So the frequency of the light had to be greater than the threshold frequency, or there would be no photoelectrons being emitted. The second thing that was believed was that the intensity of a light, so intensity of light is basically the brightness of the light. That is your brightness. The intensity of the brightness of the light will impact the kinetic energy of the electrons. So if you were to increase the brightness, it was assumed that the electrons will travel faster and the electrons will have more energy. But that's not the case. What happened in actuality was that when they increased the intensity, the number of photoelectrons increased, which since you have more electrons, you're going to increase the current. So increasing the intensity will increase the current. And the last thing that was assumed was that the photoelectrons will take some time will take some have some time delay between turning on the light and actually seeing the photoelectrons. But in actuality, the photoelectrons were released instantly. And so these predictions, they were based off the wave model of light. So according to the wave model, all frequencies of light should have been able to emit photoelectrons. But they didn't. And these predictions, yeah, again, these are from the wave model. I'll have to go through these a bit quickly just because of time. So to explain this, Einstein came to the rescue, and what he said was that a light can be modeled as this thing called discrete quantized packets of energy called photons. Or in other words, you can just imagine light to be light, just some, just imagine light to be tennis balls. Right, so you basically have a bunch of tennis balls that is hitting the electrons, and the energy of the tennis ball is going to the electrons, and the energy just gets transferred to the electrons. Yeah, and so what they found out, it was this equation. So energy is equal to h times f, where h is a constant of this value. And so what they found out is you can actually calculate the energy of light with this formula. So E equals hf. And which is why when we go back to our electromagnetic spectrum, gamma rays have the most energy because they have the highest frequency. And you can kind of see how that all is tying together. And this formula, E is equal to hc divided by wavelength, that just comes from the formula of C is equal to a wavelength times frequency. And then solving for frequency, you get frequency is equal to C divided by wavelength. Combining the two, you get this formula. Yeah, so it's the same. It's the same formula. And what's the other thing that Einstein found was something called a work function. And work function is the minimum amount of energy needed to release the electron. So, so each metal, there's a minimum amount of energy that you need for to displace the electrons. Yeah, so similar to the what is called threshold frequency. So there's a minimum amount of energy that you have to meet to actually get photocurrent. And so putting that all together, you get this. So the energy of the electrons being emitted is equal to h times f. So h times f, that is our light energy. This is and light energy, and this symbol, I don't know what it's called, but that is our that's our work function. So the energy of the electrons is essentially light energy minus work function. And whatever remaining is the amount of energy you're going to have. So what you can do is you can sort of graph it. You can graph this. Essentially, it's just a linear line. So y equals mx plus c. Instead of m, we have h, which is our constant. And instead of x, we have frequency. And because the gradient is always the same, when you graph out the energy, the lines are always going to be parallel. So in this case, we have potassium and we have magnesium. And so what you can see from this graph is as we increase the frequency, the amount of energy in the electrons will increase. Like that makes sense. As the more frequency you have, the more energy you have. And the more energy you have, the more energy is going to be transferred into the electrons. And yeah, so hopefully that makes sense. Increasing frequency, increasing energy. Cool. And then there's these things. So F0 and F0. F0 is our threshold frequency. Threshold Hz. So what this is telling us is that for potassium, you need at least 5 times 10 to the 14 hertz of hertz of light to actually create a current, right? So because everything below this, the electrons don't have enough energy to get displaced. But after your light has more than 5 times 10 to the 14 hertz, um, photoelectrons are actually going to be emitted. And because of this, the threshold frequency for potassium is 5 times 10 to the 14. So if you want to create a photocurrent, you're going to need light that has more frequency than this. And for magnesium, same thing, but instead of 5, the threshold frequency is 9 times 10 to the 14. So your light has to have more energy than this, or has to have more frequency than this, to actually emit photoelectrons. And yeah, so what we say is that the x-intercept is the threshold frequency. And the y-intercept is the work function. So the amount of energy that you need to actually displace the electrons. And yeah, so putting that together, you get this sort of line, which is just a simple linear line. Cool. If you have any questions so far, put them in the chat below, because yeah, I'll assume that I assume that everyone has a lot of questions about this, because yeah, this stuff gets a bit confusing. But what we can do, we can make things slightly more interesting. So we know that energy is equal to hc divided by lambda. You don't need to know this, but just a little aside. Energy is equal to hc times lambda, but we also know energy is equal to mc squared. And then what you can do is you can split this mc squared into mc times c, divided by is equal to hc divided by lambda. mc, that's basically mass times velocity. Yeah, so mass times velocity, which is also equal to the momentum, p. Yeah, so that combines down to p times c is equal to hc divided by lambda. You cancel out the lambdas, you cancel out the c's, and you're left with this. P is equal to h divided by wavelength. What this tells us is that light actually has momentum. So we have the wavelength, we have some wavelength of light, and that wavelength of light has momentum. Yeah, that wavelength of light has momentum, which kind of doesn't make sense, because light is by definition a massless object. And how does that massless object have momentum? That's pretty crazy to think about. But here's where things get even more crazier. What I can do is, so we know momentum is equal to h, which is Planck's constant, divided by wavelength. What I can do is I can switch the momentum and the wavelength. So now we have wavelength is equal to h divided by p. Now, this is where things start to get interesting. What this is saying is we're saying h divided by momentum is equal to wavelength. And the thing is, everything has momentum. So like this pen in my hand has momentum because it has a mass, has a velocity. So h divided by the momentum of this pen is going to give me the wavelength. Now what we just showed is that mass, or things with mass, or everyday objects, actually have a wavelength. And the thing is, you can actually prove it using, again, the double slit experiment. So what some smart people did is, so for the double slit experiment, what they did, instead of shooting light through the double slit, they started shooting electrons. So electrons, then they're traveling through these splits. And then, for the sake of time, what they saw an interference pattern, or they saw a diffraction pattern. And again, diffraction pattern, only waves, all waves can diffract. All waves can diffract. So if electrons are passing through the split and they're creating a diffraction pattern, that just proves that electrons have a wavelength. And that's pretty crazy to think about. And the same experiment was conducted on a single split experiment. It's basically the same thing, but when you pass the electrons to the single split, you're gonna get this sort of archery type of pattern, where again, this is a diffraction pattern. So you have constructive interference, deconstructive, constructive, deconstructive. So essentially, we've turned electrons into waves. And again, and because it's a wave, you can apply this sort of ratio where the extent of diffraction is equivalent to the wavelength divided by the width. So if the width of the gap is close to the wavelength of an electron, you're going to see a maximum diffraction. And so this essentially proves that that mass has a wavelength, and this wavelength is called the de Broglie wavelength, because this formula was derived by some guy named de Broglie. And so we get this. Wavelength is equal to h divided by mv, where mv is just momentum. So now what we're up to is we're saying that light has both momentum. Light has a momentum. It's a wave. It's a particle. Wave. It's a particle. And now we also show that particles are waves. Particles is also waves, which again is pretty crazy to think about. And what you can do, you can calculate the wavelength of everyday objects. So we can calculate the wavelength of a basketball thrown at this speed. So the wavelength again is equal to wavelength is equal to h divided by mv, where h is the de Broglie's constant, not de Broglie's constant, is constant. Got his name. It's some guy's constant, which is 6.63 times 10 to the negative 34 divided by mv, which is 0.6 times 5 meters per second, which gives us approximately 2.21 times 10 to the negative 34 meters. Right, so a basketball has a wavelength, and that wavelength is this. Well, the thing is, for everyday objects, this number is just so small that it doesn't matter, right? You can't make a slit that is that small that's going to make the basketball diffract, right? That's just physically impossible. So even though everyday objects have a wavelength, it's just so small that it's pretty much irrelevant. And you can do the same sort of calculation for electrons. And when you do that, you get a wavelength of 1.21 times 10 to the negative 6 meters. Well, yes, it's small. This is in the range of micrometers, and we can actually do things at this size, but this times 10 to the negative 34 is just too small. And yeah, that's why we can create diffraction patterns with electrons. Cool. Hopefully you're still there and your mind is not completely blown just yet, because we're about to get to the most confusing thing, which is special relativity. And this thing, this thing is going to completely cook your mind. So first of all, before we get into special relativity, we need to define what a reference frame is. And reference frame is basically um, your point of view in the most basic sense. So this person um, on the ground, has his own reference frame. This car over here has its own reference frame, and this blue car has its own reference frame. The thing is, from your perspective on the ground, the car is traveling at 45 kilometers, and the blue car is traveling at 50. Yeah, that makes perfect sense. But from the green car's perspective, or the green car's frame of reference, the blue car is only traveling at 5 meters per second, um, while yeah, yeah, from the green car's perspective, he's only traveling at 5 meters per second. And because of this, it's a bit difficult to compare the two. Because it's two different reference frames, you can't directly compare like what you're seeing to what the person in the green car is seeing, because it's going to be two different things. And when you get to really fast speeds, so when you get close to the speed of light, things start to get a bit iffy. Yeah, and inertial reference frame is just a reference frame that is not accelerating. And all three laws of motion will apply. The basic idea behind this is that if you are blindfolded in some dark room, and you're blindfolded in some dark room in some train that is traveling at 100 kilometers an hour, you cannot tell the difference, because again, you have no reference frame. There is no experiment that's going to differentiate whether you're at rest or you're traveling. And yeah, so when you have an inertial frame of reference, it's not accelerating, and every single laws of motion will be the same. Doesn't matter if you're traveling at 0 kilometers an hour or if you're traveling at the speed of light. Yeah, all three laws of motion will be the same. And what Einstein says is that there's two rules to his postulates. The first thing is that the speed of light is constant regardless of the motion, regardless of how fast you're traveling. So let's say if you're in a spaceship that's traveling at 0.8 c, this basically means 0.8 c means that you're traveling at 80% of the speed of light. If you just if you shine a flashlight in this direction, the light is not going to travel at 1.8 c. The light will travel at the same speed of light, which is 1 c. It doesn't matter how fast or how slow you're going. The speed of light is always the same. The next thing is that, like I said before, the laws of physics are the same in all inertial or non-accelerating frame of reference. Where the reason why we say non-accelerating is because when things start to accelerate, that's called a non-inertial frame of reference. And when that happens, we get into something called general theory of relativity. And that stuff is very complicated. Let's just say that you need a master's in physics just to understand what general relativity is. So that's why in VCE Physics, we just stick to the special relativity, where things are non-accelerating. Go on, skip this. And this is why Einstein's postulates are important. So here's the thing. We have this scenario where we have an atomic clock on Earth and we have an atomic clock on this rocket ship. An atomic clock is basically a tube where you have some electron that just keeps bouncing up and down, up and down, up and down. And like for the sake of argument, let's just say that one up and down is about 1 second. So here's the thing. When you're on Earth, the clock, like this up-down motion of the clock, is going to work as expected, right? Because you're next to the clock. It's just going up, down, up, down, up, down. But the thing is, from your perspective, when you're looking at the rocket, this this sort of electron, or like this, the clock is traveling a longer distance, right? So let's just say that in 1 second, um, let's say it travels, like the light travels 1 meter, 1 meter. When you're looking at the rocket, since the rocket is traveling, you can see that the electron is traveling a longer distance, right? So in 10 seconds, let's say in 10 seconds, the electron will travel 10 meters, like according to us on Earth. So according to us over here, the electron is going to travel 10 meters, up, down, up, down, up, down, right? But when you're looking at the rocket, what's happening is that since the rocket is traveling, you're going to see the electron travel a longer distance. So in 10 meters, in 10 seconds, the electron has traveled, let's just say, 15 meters. And the reason why this is a problem is because in the case of the rocket, light has traveled a greater distance in the same amount of time. And because we said speed of light is constant, then that's breaking the laws of physics, because light just traveled faster than the speed of light. But that's not the case. The reason that's not the case is because of something called time dilation. Yeah, I told you, this stuff gets very, very mind-boggling very quickly. Yes, essentially what's happening is because you see light travel a greater distance, time has to slow down. And then we get to this formula. It's a pretty ugly looking formula, but essentially time is equal to time zero times lambda. Lambda is just some number, and that number lambda is given by that lambda is called the Lorentz vector, and Lorentz vector is given by this 1 divided by v squared divided by c squared. Cool. So the bigger the lambda is, the bigger the time dilation is. And so first of all, you need to be able to differentiate between t0 and dilated time. And so t0 is what we call the proper time. So the time interval between two events in the same reference field, where the two events happen at the same point in space. So if we're in the previous example, if we were calculating the amount of time it takes for the rocket to leave Earth and then come back, t0 would be the time that we measure on Earth. So let's say the rocket takes, let's say the rocket takes 10 years, according to sorry. Well, sorry. Yeah. Let's say the rocket is traveling to some galaxy and it's traveling to some galaxy and it's coming back. What the person in the rocket is trying to measure is how long did it take for him to go from Earth to the galaxy and back. So t0 would be the time that the astronaut measures, because he is in the same point in space as the thing we're measuring, which is the time it takes to go to the galaxy and then come back. So the astronaut would have would be time 0. And so what we experience is the dilated time. So let's say if the astronaut takes, so using this formula, let's say the astronaut takes 10 years, the Lorentz factor, let's just say it's 2. While it takes 10 years for the astronaut to complete his journey, from our perspective on Earth, that time is going to take 20 years. Right, so I told you, it gets very, very confusing. Yeah, I don't have enough time to explain this properly. But if anyone has watched the movie Interstellar, it's kind of the same idea. So we have the astronaut guy who travels somewhere in space. And because he's traveling so far, his time is slowing down. So while he only experiences like 5 or 10 years, the people back on Earth experience 100 years. And that's why when astronauts will go to space, they will age slower than us on Earth because of time dilation. Because they're traveling at such a fast speed, their time essentially slows down relative to us. Yeah, I told you. Very, very confusing stuff. Um, and the second thing that can happen is length contraction. So while time increases, length is going to contract. And the way this works is, let's say we have some rocket that's 100 meters long. And let's say the rocket is traveling. The proper length, so the formula for this is L is equal to L0 divided by lambda, divided by Lorentz vector. L0 is the actual length of the rocket. And you can measure that if you're in the same reference frame as the rocket. So if the rocket's traveling, let's say the rocket's traveling at 0.8 c, if you are on the rocket, you're on the same reference field as the rocket. And because you're on the same reference field, you can easily measure the length to be 100 meters. But because we are the outside observers looking at the rocket, what we're going to see a a contracted length. And instead of seeing 100 meters, we're going to see a rocket that's of only about, let's say, 90 meters. And it contracts in the direction that we are traveling. So if the rocket is traveling in this direction, the length of the rocket is going to contract in the x direction. Cool. Hopefully your mind is not completely blown just yet. And the reason why this is important, right, actually has some real world applications, and it has to do with GPS. And because satellites are up in space and traveling so fast, if the satellite does not take into account the time dilation, the difference of time between the satellite and the Earth is about 6 microseconds. And while six microseconds doesn't sound like a lot, if the satellite is out of sync by 6 microseconds, which is caused by time dilation, your position on the GPS will be wrong by a factor of 2 kilometers. So that just shows that like time dilation actually has some real world impacts other than just imaginary spaceships traveling at really fast speeds. Cool. So that's about it. So I know we've covered through a lot of stuff, and a lot of stuff would have been very, very content heavy. And if you don't understand a lot of the stuff, especially with special relativity, because I didn't get much time for that, sorry. But again, if you don't understand everything, that is perfectly fine. Like I understand that this is some really heavy stuff. But hopefully you at least have a decent understanding of the basics. So when you go back to school, that you'll be able to learn the topic a lot better. And yeah, so basically what we've gone through all of this: double slit experiment, the photoelectric effect, wave particle duality, wave particle matter with the electrons, and also special rel. Yeah, so I guess that's everything for these 2 hours. And hopefully you were able to get something out of it. And we hope to see you in the next not Head Start lecture, but next exam revision lecture, which will be around, I'm assuming September, October-ish. Yeah, and if that's everything I guess that's everything for today. So yeah, hopefully you learned something, and we hope to see you sometime later. See ya.